So continuing on with our discussion of auto rotation, in parts I believe 2 and 3, we looked at the aircraft's performance in a vertical auto rotation, essentially where the aircraft is coming straight down, zero airspeed, vertical descent auto rotation. So since we're at zero airspeed, there really is no dissymmetry of lift. All right, as we're coming down, the left and right side of the rotor disc are producing the same amount of lift. So it's just like sitting here in a hover at zero airspeed. There is no dissymmetry of lift until you start moving forward. All right. So let's look, and essentially the same thing occurs in an auto rotation. If you remember, we looked at this illustration here, and this is for a zero descent auto rotation. And if you remember here, from the root of the blade out about 25% is the stalled region. The next 50 to 60% of the blade or so is the drive-in region, and then the very outer part of the blade is the drive-in region, right? And again, no dissymmetry of lift at a zero descent auto rotation. However, as we start moving forward, that changes. So again, here's the same regions, all right? But what happens as we start moving forward is all three of the regions start to move towards the retreating side of the rotor disc, right? And so let's start looking at the stalled region first. If you look at the stalled region, you'll see that there really is now, with forward airspeed, there really is no appreciable stalled region on the advancing side. And both the driving region and the drive-in region have got quite a bit larger. Over here on the retreating side, the stalled region now has got considerably larger. The driving and drive-in region have gotten considerably smaller. So obviously you can see that we're producing a lot more lift now on the advancing side than we are the retreating side. So again, teetering has to occur to compensate for the two. In fact, the amount of dissymmetry in an auto rotation for any given airspeed, the amount of dissymmetry is always greater, and therefore the teetering is always greater for any given airspeed in a stabilized auto rotation. All right? Now you know why your V&E is decreased in an auto rotation, and your auto rotation V&E is fairly significantly reduced, and we'll actually look more specifically at that here in just a bit. Okay, so you guys probably remember at zero airspeed, the amount of drag on the rotor is quite high. As we start moving forward, the amount of drag for the amount of lift produced continuously decreases, so that as we get faster and faster on our airspeed, the amount of drag produced by the rotor disc is ever decreasing, right? Parasite drag, the amount of drag that's produced by non-lifting surfaces such as the body of the helicopter, the skids, and that sort of thing, again starts at zero airspeed, but increases with ever increasing airspeed. Parasite drag increases, and it's a little bit of a linear increase as well. So if we were to plot those two drag lines here, this blue line here being the amount of drag as we increase in airspeed, the amount of drag reduction that occurs from induced drag by producing lift, and also the amount of parasite drag as with forward airspeed, we're going to increase our parasite drag. And so this line here is the average between the two, right? And where that drag line is lowest at is going to be your minimum descent rate. Well, it doesn't matter that if we're in powered flight or if we're in unpowered flight, these drag changes occur just the same, whether powered flight or unpowered flight. So interestingly enough, as we increase from zero airspeed in a auto rotation, as we increase our airspeed, the amount of sink rate is going to start to significantly decrease, right? And so they've got a curve here, and this curve is actually for a Sikorsky 300. But all helicopters are going to have a similar curve that shows sink rate in an auto rotation. And here at the bottom of the curve, where the amount of sink rate is the least or the lowest, will be where your minimum descent speed is going to be. And for the R-44, it would be at 55 knots right here in the center. For us to go slower than 55 knots in an auto rotation, then as we go slower and slower and slower, our sink rate is going to be ever increasing. And for us to go faster in an auto rotation, as we increase our forward airspeed, again our sink rate is going to increase. So it sort of begs the question, well, why do we do an auto rotation in an R-44 at 70 knots instead of 55 knots, instead of 55 knots, which is the minimum descent speed? Well, it's because of kinetic energy. And again, what we're doing in an auto rotation ultimately is harvesting that kinetic energy, good old energy of motion, and using it to produce stopping power both in forward motion and in producing lift to reduce our descent rate, right? So if you look at the amount of kinetic energy that we have at 70 knots versus the amount of kinetic energy that we have at 55 knots, it's considerable. Again, it's mass times velocity squared. If we square 55, 55 squared is 3,025. If we square 70, that's 4,900. Well, if you divided your 4,900 by your 3,025, you get about 1.61 or so, about a 60% increase in the amount of kinetic energy. So the amount of kinetic energy that we possess at 70 knots is 60% greater than the amount of kinetic energy at 55.